today we're going to talk about the basics of probability. And probability is kind of a core topic in data science, of course, and really up to this point in the course, we've mainly avoided all mention of probability for the most part. I mean, I mentioned it a little bit at times, like with our N-gram models, we talked about a little bit, but I never really formally defined probability and kind of what we mean by things like random variables. So I'm going to do that today. We're going to go through some basics of probability today. And then next time, actually, it's going to be a little switch. Next time, just to break this out a little bit more, we're going to talk about statistics and things like maximum likelihood estimation and a naive Bayes. And that's going to be next lecture. This lecture is kind of the basics of probability. So before I get started, a few quick logistics. First of all, this is what I mentioned before, but the next few lectures, they're going to be as normal, but you may have a harder time hearing me than normal for classes. So the other bit of news is that the final project that was released actually at the beginning, was the middle of last week. There's a note on it on the course website. If you haven't seen that, please go ahead and look right away. We have the deadline currently scheduled for this Friday for the proposals. The proposal is very short. It's like the tutorial proposal. It's a little bit longer. It's like 200 words, I think. But it's short, but the idea is you actually are supposed to form your groups by this Friday for the final project. It's groups of 2 to 3. In rare occasions, I can approve a group of 1 if there's a need to for any real reason. Groups of 4, don't do that. Just break into groups of 2 instead. The link to actually submit the proposals will be up on the website by either the end of the day or the end of tomorrow. Lastly, I got a lot of emails back about tutorials. So I emailed everyone. I got a lot of responses back. I think I replied to most of them. But if I did not reply to you, and I don't reply to you by the end of today, send me an email back, please. I just missed it somehow and I didn't get to it. And please email me back if I have not responded to your response by the end of today. Also, if you haven't gotten information, period, also let me know. Okay, any questions on that? Yeah. Projects are a little bit more open-ended. The question was, can they have examples for projects? Projects are a little bit more open-ended. So I haven't in the past given examples for projects, because it's also more standard to have projects for a class. I think that given what's in the document, I kind of want you to explore. You're welcome to email me for feedback about whether you think it's appropriate or not. And I'll give feedback also on the proposal itself. So I will give you the feedback, and you can adjust also. But the longer you wait to adjust, the less time you'll have. There's another one up there somewhere. Okay. All right, let's get started. So there's really going to be a few basic things here. We're going to cover first just a few slides on probability in data science. Why do we care about probability in data science? We're going to talk about some basic rules of probability. This is actually going to be the majority of the lecture. It's just the sort of fundamental rules of probability. We will use them now going forward, and so I want to define these things a little bit more rigorously than we have so far in this course. And lastly, we'll talk about some common distributions that you may want to be familiar with, the probability distributions both for discrete and continuous random variables that you probably want to be at least vaguely familiar with. Okay, so let's start by talking about probability in data science. Now, as I said, up to this point in the course, we've really focused largely not on any probability, which is kind of surprising in some sense because, a lot of machine learning, though we presented it from an optimization standpoint, it also has just as equally valid a probabilistic standpoint. And we'll actually talk about that next lecture, not this one, but the next lecture. But this is no longer the case. At some point, we have to sort of delve into probability, and that's going to be this lecture. So the other thing that people sometimes don't sort of mistake is the difference between probability and statistics. So there are lots of differences, of course, but for the purposes of this course, statistics is probability is about sort of random occurrences, random events. And statistics is when data comes in the mix, right? So if you're talking about sort of modeling random events just from some sort of, from some parameters, that's the domain of probability. But if you're talking about now fitting kind of distributions to observations, That's the domain of statistics. So this lecture is going to be about probability. But next lecture, we'll talk about statistics, about how you actually do things like fit distributions to actual observations of data. So why do we care about probability or statistics here? And the fundamental reason, I think from a data science, there's lots of reasons you might want to, of course. But from a data science perspective, the fundamental reason is that a lot of the events we see in the world or can model in the world are fundamentally uncertain. So consider our example we talked about before about predicting peak demand from high temperature. So we showed this plot, and this plot's kind of nice because it's really quite, it's pretty well contained on a line, or in the case of the nonlinear case, on a curved surface. But of course, for any given temperature, there really is, and you can actually break this down a little bit more by doing things like looking at weekdays and weekends, which we saw also. But for any given set of features that we can have access to, there is going to be fundamentally some uncertainty about how much demand there's really going to be, right? We don't think that this is a deterministic quantity. It depends on, right? As long as we have free will, I can affect how much electricity there's going to be in Pittsburgh tomorrow. I can choose to plug in a light or not. So if you believe in human free will, there's nothing that we can do at our level of modeling to actually remove all uncertainty from that equation. It's kind of amazing we can do as good a job as we can, but we can't remove all uncertainty. And so when you talk about kind of making predictions or modeling real events, real data, you need to understand some notion of probability and randomness that's involved in this data. And that's really where probability from a data science perspective enters kind of our purview. So because of that, I'm going to take a detour now, and this is going to be kind of a self-contained lecture for the most part, but it's going to be basically a run-through of the basic techniques of probability. And what I actually have found is that one of the hardest things about probability for people that are sort of, even if you've seen it a couple times before, is just getting used to the notation. Because probability notation is, for some reason, actually quite confusing. I think it's very sometimes imprecise, and even the notation I use is quite imprecise, I'll admit. But I'm going to try to make it as concrete as possible so that you can understand what I mean by things, even if the notation seems kind of weird in retrospect. And then we'll talk about some common distributions later. But let's talk about some basic rules of probability. So for this course, we're not going to delve into the actual kind of mathematical definitions of probability. So if for the people that hear that are mathematicians, right? This lecture is going to likely bore you and maybe confuse you because you have a very different notion of. It keeps cutting in and out a little bit. Hopefully it'll be okay. You have a very different notion. Things like random variables are actually functions, and you think of outcome spaces and sample spaces, this kind of stuff, right? And we're actually not going to really talk about probability at that level. We're going to talk about it much more at a level that people typically use to manipulate probabilities. What you typically have to do when you're actually writing, or making derivations in a data science context, is you have to manipulate probabilities, right? You have to apply things like Bayes' rule, which we'll talk about. You have to apply things like conditional probabilities. And you want to use these rules to actually manipulate things and come up with new expressions. And so I'm going to describe probability at a level, on a level, which is typically used to actually manipulate those expressions. So with that being said, this is a very kind of informal look at probability. It is not a rigorous view, but I think it describes the right level of intuition for most of the work you actually do in data science. So the sort of starting point for probability is this notion of a random variable. And again, we're not going to define this formally. We're just going to sort of say that informally, a random variable is a variable whose value we don't yet know, right? But it has some probability under which it takes on different values. So for example, the weather tomorrow, right? That could be a random variable because we don't know what the weather is tomorrow. It can take on different values. And we might say that it takes on the values of sunny, rainy, cloudy, or snowy. These days it could be all of those. I have no idea what it's going to be. And maybe the probability that sunny is 0.3, probability that rainy is 0.2, et cetera. And each of these, of course, are a number that assigns a probability to it. It probably has to sum up to 1. Okay? And so that's really the level at which we're going to think about random variables, right? We will need a little different notation for continuous random variables, which we're going to discuss shortly. But this is what we'll use for now. Okay, so in this class, we're going to use, at least for this lecture, later lectures might actually deviate from this a little bit, and I apologize. The notation here does sometimes just get more, people tend to use sort of what's used in the field rather than what's used in probability. But for this lecture, I'll be consistent with this. So random variables, to denote random variables, we're going to use uppercase letters. So for example, the letter X, or if it's a word, we'll use the uppercase word, like weather with an uppercase W. But oftentimes we'll just use a symbol like X to denote a random variable. And X now can take on different values, right? So for this example, suppose, for instance, X takes on the values 1, 2, or 3. In this case, this notation here, P of X, is kind of actually weird. Because normally, you think of P of X, right? Something like P of X being a function of X. But usually, when people say P of oops, this is, oh, come on. Just got this pen. Okay. P of big X here is actually, you should think of it like a function, or like a dictionary, really, a mapping from values that this variable takes on to outputs. Now, this is sort of informal here, because we're not going to call this as a function. It's just that this notation here means the entire probability distribution of the random variable X. Okay? All its values it can take on. So you should think of this like a dictionary, with the 1 being mapping to the value 0.1, 2 mapping to the value whatever. But it can also have values like sunny or rainy or cloudy, right? Or keys like that, right? So it could have a key of 1 that maps to 0.1. Sorry, a key of rainy that maps to 0.1, a key of cloudy that maps to 0.2, etc. So it would probably be better to call it something like this, like P subscript X, to emphasize this is a function, right? It's not a scalar value or anything like that. But this is more common. Just refer to the entire distribution as this P of X. Now, in addition, though, this is where things get a little confusing. We're going to use lowercase letters to refer to particular values that this variable takes on. So for instance, and this is especially confusing because sadly, we write things like X's and Y's, and a big X and a lowercase x when I write it look very similar. I will try to differentiate. If you can't tell which is which, let me know. On the slides, it should be more obvious. So this is a big X here. P of little x, that is actually a number. In fact, it's a positive number between 0 and 1. Really, actually, I should say it like this. It's a number between 0 and 1. So, and this is also, we will equivalently write things like this sometimes. This is also equivalent to saying the probability that x equals little x is both equivalent. And those are numbers, right? Those are actual probability values that this thing takes on. And I'll give us some examples in a second. But basically, if we want to sort of know what a single entry is here, that would be the normal sort of function we're used to, where we input an actual value it can take on, i.e. a key, and we get out the actual probability. Okay? Now, what makes this fun is when you can mix and match things. So if we have two random variables, and again, I spend a lot of time talking about this because I think this is actually the thing that confuses people the most when they see notation and probability. And so I kind of want to just hammer this home, and apologies if it seems kind of obvious. So if we have two random variables, say x1 and x2, x1 takes on values, say 1, 2, 3, x2 takes on values 1 and 2, then x1, x2, so this thing, refers to the joint probability distribution over both those variables. So what this would be a function, really a mapping, from all possible settings of both values to a number, right? Because when you specify a probability distribution over two variables, you need to specify what happens, what's the probability of each possible combination of values to those variables. So I would need to have one, this would basically be equivalent to saying this is 1, 1, 1. That has probability, say, 0.5. 1, 2 has probability 0.1, etc. Right? You just enumerate all possible settings. And again, of course, P, these are big X's here. P of little x1 and little x2, that's just a number again. It's a number in 0, 1. It just corresponds to the actual entry there. Where this gets kind of confusing is when you have sort of mixed and matched things. So for example, the probability of x1, x2, so that's big x1, little x2. That is a specific value for x2, but sort of a generic value for x1. So that would actually be a dictionary over values in x1. And importantly, that one's actually not a distribution because it doesn't sum to 1, right? We've just cut out half the values from it, and it will not sum to 1. I'm going to give an example of this in a second, but I will say that because a lot of these things do not actually correspond to real probabilities, we call them kind of generically factors. So factors are these kind of arbitrary dictionaries that are mappings from keys, the values a random variable can take on, to probabilities, or I should say to numbers in 0 and 1. Okay, so let's look at an example here. Hopefully this will make it a little more clear. So suppose now I have actually 2 random variables. The weather, I'm just going to cut it down to just to 3 categories: sunny, rainy, and cloudy, and a cavity variable, whether I have a cavity or not. So people can say they can tell what the weather is going to be by how their tooth feels, right? So maybe whether I have a cavity or not will actually influence what the weather is going to be tomorrow. So if I want to talk about the joint distribution of the random variables weather and cavity, what that would be is a function that basically maps from every possible combination of those values to a probability. And these sum to 1, of course, right? We add these all up. This is a full joint distribution over those 2 things. It sums to 1. If I want to find, the probability of sunny and yes, I could also, by the way, a little bit more explicitly, if I wanted to be sort of easier to understand, maybe I could write the probability. I could write that same thing there as the probability of weather equals sunny and cavity equals yes, right? And that's, again, a number. In that case, we just look up the entry there. That number is just 0.07. And this is where it gets kind of tricky, is when you have combinations of both. So the probability of weather and cavity equals yes. Is this sort of mapping, right? You just select out the terms that correspond to the known entries there. But of course, this does not sum to 1 here. If we want to make it sum to 1, we can normalize it. That makes it a probability. In fact, that is a conditional probability, which we'll talk about in a second. But this is basically the notation that we have here. Okay, so let's talk about the last thing I want to mention is operations on these probabilities. This is where things get confusing because they're actually quite simple, but they're simple, and the more you think about it, the more confused you can get sometimes about these things. So if I have some factor, piece of paper, which is over 2 variables. So say I have some factor. And I'm going to use P there, even though it does not actually have to be a probability. It could be something else. X1 and X2. And I run some operation between it and another factor. So this could actually be division, it could be multiplication, it could be a lot of things. Let's just sort of multiply it by their factor of P, X, 2, and X3. Okay. This product is now a factor over all 3 variables. So this product would be a mapping from settings of all 3 of those variables to some number. Okay, where the value of that mapping is just equal to, well, you just plug in the values of the original, all the different variables into their factors and compute that. It's really kind of the simplest thing you can imagine, but it's important to note this is what's happening here. And I'll be more concrete about this when we talk about things like conditional probability or even independence, because these will come up when I write simple looking rules for independence or conditional probability. But it's important to know that what's going on is you're really sort of, these expressions are kind of creating operations on these factors or on these probabilities that are leading to other they're leading to other sort of factors. Okay, so hopefully that's somewhat sensible. But if not, I think it'll make much more sense when we talk about some particular examples. Or even just not even necessarily concrete examples, but just examples in terms of definitions that you may be familiar with in probability. Okay, so let's now jump. So now what we're going to do is we're going to go through a bunch of rules, sort of basic rules to probability, that kind of define the basics that you will typically use when you manipulate probabilities to try to make inferences essentially. And that's largely the goal of probability, as I said, in data science. So the first thing we're going to mention here is the notion of conditional probability. So the conditional probability, which is written as the probability of x1 given x2, is just defined as the probability of x1 and x2 divided by the probability of x2. These are all capital letters here that I'm writing. Okay. And so again, a few things to point out here. This term here is a factor, right? It's a function where you can input any value of x1 and x2 and it will tell you a number. But it's not actually a probability itself, right? Because the sum over all possible values of x1 and x2 are not actually equal to 1. It really is a factor. And some of those terms are probabilities, in fact, but kind of it's important to understand that these things, this is a conditional probability, which is not the same as a normal probability. But it's still a factor in that it's still a mapping from all possible values of x1 and x2 to some number that defines the conditional probability of x1 and x2. And what this really means is that if I want to compute, and again, this is sort of just notational, but just sort of important to kind of remind yourself about this, is if I want to know, what's the probability that x1 equals some little value x1 and x2 equals some little value x2, this just means you just substitute these things in there. So it's just equal to the probability that x1 equals x1 and x2 equals x2 divided by the probability that x2 equals little x2. Okay? And so for any setting of x1 and x2, I can of course plug these into this equation here. These are all just numbers now because they're all just the instantiated version. And I can do that to get a factor that describes my conditional probability of any value of x1 given any value of x2. Okay? So from now on, I am just going to kind of stick to this notation here because it hopefully is obvious like what this is implying about things. It really is the obvious thing, nothing unobvious. But when you sort of go through the first time and you try to actually implement this, some things can be kind of confusing. How do I implement conditional probability like in Python? It's actually not completely obvious. You have to just go through it and figure out how to do it. And so hopefully, as you do that, it'll kind of this notion of what things are factors and what things are numbers will make a little bit more sense. Now, importantly, this thing can also be written the following way. It can also be written as the probability of x1, x2 equals, I'm just rearranging these terms here, equals the probability of x1 given x2 times probability of x2. All right? But of course, there was no necessity for me to do it that way. I could also write it the opposite way. This thing also equals the probability of x2 given x1 times the probability of x1. Right? And so this will actually come back to us in a second when we talk about Bayes' rule. But I want to highlight the fact that this is just sort of, these things are both equally valid here as ways to write probability distributions and conditional probability. All right, any questions so far? Okay. So the second sort of thing we're going to talk about is marginalization. And marginalization is a way we can get marginal distributions over some, what are called marginal distributions over some variables given joint distributions. So did I use these terms before? I forget if I used these terms. Yes. So I called P1 and P1 P of x1, x2 a joint distribution. If I just want P of x1, I'm going to call that a marginal distribution. It's a distribution that's just over one of the variables. And the rule of marginalization says that the way I get this is I sum over all possible values of x2. So that means this is little x2 up there. I sum over all the values of it of the joint probability of x1 and x2. Okay. And of course, I can also write this a little differently. I could also write this as the sum over all x2 of the probability of x1, big X1 here, given x2, and probability of little x2. And so you can do the other way too, of course, as well. But it's sort of important to understand that these things can all be manipulated in this way to give us different ways of writing the same expression. Okay? But all that's happening here is we're sort of summing over all possible values of x2 to get the probability of just the values of x1. Now, let's say these are all binary valued, right? So they all have sort of two, all can take 0 or 1. How big? I mean, what is that middle term there? P of x1, comma, little x2. What is that? It's a factor to say? How many different inputs can it take? Or how many different values does it take? 2, right? Because we specified an actual value for x2, and x1 is still, you have to specify all possible values of that. Okay? So just think when you just like when you do matrix operations, what you should always do is write the sizes down to understand what's going on. The probability is just sort of write what things are being specified and what things are being are being specified directly, and what things are kind of left generic, to know how big of a factor you have left. This same thing, of course, generalizes to joint distributions. So you can have, over many variables. You can actually, if I want the joint distribution from x1 to xi, and I have a joint distribution over all xn, I can just sum over all possible values of the later variables. These kind of operations are going to be important later when we talk about Bayesian networks. It's not till later in this course. It's not going to be this set of lectures, but it will be. This notion of sort of chain rules and sums and marginalization are going to be very important when we talk about Bayesian networks. Okay, so moving along, the next topic, which you've probably seen before, I would imagine, is Bayes' rule. So Bayes' rule is actually just a trivial manipulation of conditional probability. So it actually falls exactly out from this thing here and from marginalization. So it's just a simple sort of merging of these two rules. And all it does is, what Bayes' rule does is it gives an expression, a way to compute a conditional probability of P of x1 given x2 in terms of the opposite conditional probabilities, P of x2 given x1, and the prior probabilities on x1. So in particular, if I want to know P of x1 given x2, let's make sure I have the right order here. This is equal to P, just by definition of conditional probability, P of x1, x2, P of x2. That's just over P of x2. That's just the definition of conditional probability. I'm going to now rewrite this term in terms of this expansion here. So, and I'm going to write this term here in terms of marginalization. So this is equal to P of x2 given x1 times the probability of x1, divided by, I'm going to marginalize out over x1 here. So I'm going to sum over all values of x1. It's easier to read the slides here than my handwriting, because the little x1 on the denominator is the only small x1 here. The rest are all big. The probability of x2 given x1 times the probability of x1. Okay. So now here's the example that everyone uses when we talk about Bayes' rule. This is going to be a poll. So the example is, I want to know if I have a certain strain of the flu. Also a topical question like the weather is these days. And it's a rare strain of the flu, not like the one that's currently going around, which is sadly not that rare. It happens only 1 out of every 10,000 people. But fortunately, there's an accurate test for this flu. In other words, that if I have this flu, it will tell me that I have it 99% of the time. And if I don't have it, it will tell me I don't have it 99% of the time. So I go to the doctor and I test positive for this flu. And the question is, do I actually have the flu, or what's the probability that I actually have the flu? And I actually even give some approximate results here on the Piazza poll. So the Piazza poll actually says, is it approximately, you don't have to get it exactly, but is it approximately 99%, approximately 10%, approximately 1%, or approximately 0.1%? So we'll open the poll, think about that for a few minutes. Let's take a look. All right, so mixed responses there. Slight majority in this one. Does anyone want to chime in about why they picked their particular answer?
So we can split this into different parts, right?
Mm-hmm.
So the probability that you have the disease is 1 over 10,000. So that means if you don't have it, it's 9,999,000, right? And then that being correctly classified as 99% or 99 and 100, right? And so for each one, the branches are going to split up.
Mm-hmm.
So the options where it is going to be the probability that you have the flu is when you think you have it and it's correctly diagnosed, and when you think you don't have it and it's incorrectly diagnosed, right?
Mm-hmm.
So that gives you 99 over 100 times 1 over 10,000 plus 9999 over 10,000 times 1 over 100.
Okay. Maybe this is a bad question to ask for an explanation for. That's correct, but maybe I'll just write it out. It's not the easiest thing to write, or to say verbally. So the verbal explanation, by the way, so it is 1% is the answer. But by the way, you shouldn't feel bad if you don't get this, because so there's one of these articles every few years or so. Doctors don't know this either, apparently, which is really sad because they actually run tests like this. So the answer is 1%, and when you ask doctors, they usually say 99% also, which is, something that they should probably teach doctors at some point in their medical school, but who knows how accurate these shock articles are too. They might be a little bit overstating the case. Okay, so what's happening here? Actually, let me bring this down, because it's actually quite easy. So let's sort of do this. Okay, so let's say that the random variable x1 corresponds to do I have the flu? And x2 corresponds to testing positive for the flu. Okay, and they each can take on values 0 or 1. What we would like to know is just this quantity, right? We just want to know the probability that I have the flu given that I tested positive. But we don't have any sort of table that tells us that. So we're going to actually apply Bayes' rule to express this in terms of things that we do know. Okay, so we know that we know that the probability that x1 equals 1 was the probability that I have the flu, given that x2 equals 1, I tested positive. This is going to be equal to, I just plug in these terms here, so the probability of x2 equals 1, given that x1 equals 1. Now, importantly, this term here is the probability that I test positive given that I have the flu. And that we do know. That's 99%, right? That's 0.99. Times the probability that I have the flu. We have that too. That's just the prior probability I had the flu, irregardless of tests. We have that. It's 1 in 10,000. Okay, so this term here is 0.99, and this term here is 0.0001. All right, now we divide by this denominator term here, which is going to be first the probability of x2 equals 1, given the first value of x1, which is x1 equals 0, times the probability that x1 equals 0, plus the next term, which is now x1 equal to 1, plus the probability x2 equals 1, which is given that I have the flu. So I probably should say it in terms of the actual quantities here. So this is the probability that I have the flu, given that I test negative. Given the probability that I test negative, given that I don't have the flu. Test positive, given that I don't have the flu. Times the probability that I don't have the flu. Plus the probability that I test positive, given that I have the flu, times the probability that I have the flu. So the probability that I test positive, given that I don't have the flu, that's just the opposite of this. That's just 0.01. The probability that I don't have the flu is 0.9999. Okay. This one's just the same as the top there. That's 0.99. This is 0.0001. And if you just compute this, this is about 1%. Okay, so this is how you derive this expression here. Yeah?
What you did and what that guy said are actually pretty different. Were those correct?
I think it's hard to describe what I did versus what he said, because
Like sort of adding the joint probabilities where the test is positive.
I think he was basically, I think they're equivalent, but maybe not obviously so. So I suspect he was probably looking at like combining those joint probabilities, like not marginalizing them out in terms of conditional probabilities there, but kind of doing that step kind of in his head. I think that's what was happening. I'm not sure. It's very hard. I probably should have just written it down. Because I mean, it's just hard to describe. Even this would have been very hard for me to describe kind of vocally. So the point here, though, is that sort of the take-home message is that even if you test positive, there's a very low chance of actually having the flu, because the prior probability of having it is actually much smaller than the false positive or false negative rate of the flu test. So if I test positive, chances are I'm actually a false positive, not that I actually have the flu. Right? And this is actually a very common thing when the occurrence of some disease is lower than the false positive rate or false negative rate of the actual test. Okay, so this is a nice application of Bayes' rule. You will almost certainly see on some tests an example like that again. So commit that to memory, and if you did guess 99%, remember this sort of derivation and kind of why it makes sense to think about Bayes' rule in this context. Okay, so moving on. Independence. Another thing that's more important to understand conceptually, frankly, than to just know the math. Or rather, you have to know the math, but it's very important to have a conceptual understanding of this. So we say that random variables x1 and x2 are what are called marginally independent if their joint distribution is equal to the product of their marginal distributions. Okay, so in other words, x1 and x2 are independent if p x1 x2 is just equal to p x1 times p x2. And again, think of this like these are both factors, right? So this is a factor over all possible settings here of x1 and x2, and this product is also a factor over all possible settings x1 and x2. but it has to do with their independent marginal distributions, whereas this is just the actual joint. So another way of writing this, which is actually frankly a little bit more intuitive to me, is to say this is also equivalent to the fact that P of x1 given x2 is just equal to P of x1. And really, that's now, when you think about what that means is that for any setting, what I really mean by that, because this is a factor over two things, this is a factor over only one, what I really mean is that for all, what this really means is that for all x2, P of x1 given little x2 equals P of x1. Okay, that's what that really means. And so what that's saying on some level is that knowing x1, or knowing x2 does not help you figure out what x1 might be. So, if I have to guess, if the, say the, well, I guess we'll have an example in a second, but if there was no dependence between, the peak demand tomorrow and, say, having a cavity or not, what that would mean is that if I tell you whether I have a cavity, that doesn't help you infer what the, whether or peak demand is going to be like tomorrow, right? Whereas if they are not independent, they're dependent, then if I actually tell you whether I have a cavity or not, that can help you in your prediction of what the weather is going to be like tomorrow or what the peak demand is going to be like. So let's look at this. Let's do one more quick poll. This is actually an easy one. But with this setting here of variables, are the weather and cavity variables independent? So about 2/3 and 1/3 say they're not independent, 2/3 say they're independent. Does anyone want to maybe a quick explanation, not like describing the the math of this equation term by term, but is there a quick reason why someone says they're independent or not? Yeah. Okay, they're not independent because the probability of it being sunny changes when I see. So, like, if it's sunny and no, that probability is 0.63, and sunny and yes is 0.7. So different, so they're not independent. Okay. Does anyone else want to chime in? Yeah. Okay. So you sort of eyeball it, and you can kind of see. I guess you're saying yes, they are independent. Okay. Yeah.
I don't think you're seeing that the probability of sunny given and yes or no changes depends on yes or no. It says that they're dependent because like it could be that they're still independent, and then those two probabilities are just the probabilities of sunny. Oh, it never is right.
Mm-hmm. Yeah. Mm-hmm. Yeah. Okay, I like that one actually. That's good. So they think they are independent? Okay. Yeah. That's probably the way I would go to it also actually, to eyeball it. But let's actually do this formally. Let's look at sort of formally what these things are. Well, maybe I'll spend a little time on this. Okay, so first of all, we have our distribution here, right, of all possible things. And so, again, I kind of like this definition of conditional independence the best. So I want to compute the probability of the weather given, say, cavity equals yes. Okay? That's what I want to sort of compute right now. Okay, so let's think about what that is. That's the probability of the weather being sunny and cavity being yes. So that's weather sunny would be and then divided by the probability of cavity being yes. Well, see, first let's compute the probability of cavity being yes, right? Cavity equals yes. You just sum up, over all these ones where it's yes, and you get the probability of a cavity being yes is just 0.1, right? Does everyone see how I did that? That one's easy. That's just I sum up all the entries in that table where cavity is yes. Probability of cavity being yes equals 0.1. So the probability of whether given cavity is yes. I shouldn't have raised that. So sunny, that would be 0.07 divided by 0.1. So it would be 0.07 divided by 0.1. So that equals 0.7. You can sort of see the pattern here, but rainy would be 0.2, and cloudy would be 0.1, right? So this is the breakdown that we have for the probability of weather, given that the cavity is yes. And we do the same for cavity being no also. I won't do it. You'll find these are the same thing, but you do the same thing. You probably cavity equals no, that's just 0.99. I would divide each of those terms by 0.99 to get the same term. Furthermore, if I just want to say P weather, this would just say, well, this probability of it being sunny is what? It's just the sum of these two things, right? Sum of those two things. That's also 0.7. And rainy is the sum of the next two things, which is 0.2, and cloudy is 0.1. So these are in fact independent, and the way you can see that, or the way that I find sort of easy to see that, is to say that the marginal probability here is the same as the conditional probability given cavity. I've just only shown it for yes, but you can do it for no as well. I mean, you usually don't have to in this case, but if you have many variables that can take on, you have to do it for every setting of the variables. Okay, so they are independent, but this also sort of is an important point. So the fact that variables are independent does not mean that their joint probabilities are the same, right? It just means that so that these don't change. Just like rainy and yes is not the same as sunny yes. You don't have to have those things being equal to be independent. What is important, and I think I won't highlight the ratio sort of argument here, but the idea is that the actual distribution described by this joint distribution does factor in this way. So basically, it can be expressed as the product of these two independent marginal distributions. Okay. The next thing. So again, this is something you have to kind of just grind through when you actually have an actual distribution here to sort of see if it's independent or not. But the key point is that this notion of independence means that given information about cavity, it doesn't change my distribution over weather. Right? That's the key point, is that this quantity here is the same as this one. So in other words, if telling me whether I have a cavity or not won't help me predict the weather any better. Okay, so now we move on to a little bit even more confusing topic of conditional independence. And again, the definition here kind of hides the trickiness of this. So the definition is it looks a lot like independence just for the conditional case. Or is it? I didn't actually derive why these two things are equivalent. Does everyone follow this derivation here? So if this is, so here, to show this is equal to that, right? All I do is I first just plug in the definition. I use the fact that this is equal to the product of those two things, and those two cancel out. So therefore, it's just equal to P of x1. Okay, so let's talk about conditional independence now. The definition, again, looks pretty simple. It says if I have three random variables now, I would say that x1 and x2 are conditionally independent given x3 if the joint distribution there is equal to the product of the two conditional distributions, x1 given x3, x2 given x3. And using the exact same kind of math as before, we can say that the probability, this is also equivalent to saying that the probability of x1 given x2 and x3 is just equal to the probability of x1 given x3. Okay. What this means is, if I already know x3, so x1 and x2 actually might be, they don't have to be independent. We'll get to that in a second in the next slide. This is actually a very important point, that conditional distribution independence does not imply marginal and vice versa. But the point to this is, if I know x3, I want to predict x1. I know x3. Then also telling me x2 doesn't actually help me. So just like before, telling me x2 didn't help me predict x1 better. Here, telling me x2 doesn't help me predict x1 better as long as I already know x3. So this is again, I'm just using like letters here, x1, x2, x3. Let me give a few examples. And the thing I actually want to emphasize here is that conditional independence does not imply marginal independence, and marginal independence does not imply conditional independence. So to illustrate this, I'm going to give an example, and I'm actually not, this is like this classical example of a Bayesian network that everyone uses in every textbook in the world. I'm actually not going to describe Bayesian networks yet. I'm just going to describe this as a story. So the story is, there's two rare events that can happen, an earthquake or a burglary at your house. These are independent events. So, there's just some probability of an earthquake happening or a burglary happening. Both of these, though, have a very high chance of setting off your alarm, like your fire alarm, or I guess your home alarm. Okay, so that's the top half of this chart here, saying that the earthquake can cause the alarm or the burglary can cause the alarm. We're not going to worry about the actual semantics of this, what is actually a Bayesian network here. That will come much later in this class. In addition, when the alarm goes off, there's some chance that your neighbors will call you. Each of your neighbors, you have two neighbors, Mary and John. And if the alarm goes off, then independently, they each flip a coin and say, okay, if the alarm's going off, I'm going to call me with probability, say 0.5 or something like that, right? If the alarm is not going off, they don't call me. Or they call me maybe very, very rarely. Okay, so that's the story. So the important things to sort of keep in mind here are the conditional independencies here. So here, I'll just write it out. Here, earthquake and burglary are marginally independent. That is, the probability of there being an earthquake is the same as the probability of an earthquake given as a burglary. There being a burglar doesn't raise the probability or affect the probability of there being an earthquake in any way. Right? So these are independent. So you had this. So this means that earthquake and burglary are marginally independent. But, and this is sort of the really subtle but important thing, they are not conditionally independent given the alarm. Okay, so I actually don't really care about sort of writing down the formulas here. You can do that if you want, but the important thing is the intuition here. Okay, so here's the scenario. So say that your alarm is going off, right? This should raise the chance that, you expect there to be, say, an earthquake. This should raise the probability of there being an earthquake if the alarm is going off. So I could ask, maybe I should say earthquake equals 1, given alarm equals 1, right? That raises the probability of the alarm, but I'm saying this just because I'm just talking about all the probabilities here. So, right, so if the alarm goes off, there's a higher chance of it being an earthquake. There being an earthquake, right? because the alarm goes off and there's an earthquake. So it's probably a higher, it's not, maybe not super high, but for the same Bayes rule reason, but it's a higher chance than if there's no alarm at all. But if I tell you, so maybe you'll have some. If I tell you the alarm's going off, you'll have some notion of how likely it is that the earthquake's happening. Don't worry about the actual numbers here. But if I tell you the alarm's going off and there's a burglary, this should actually change your opinion whether there's an earthquake or not. Right? And the reason is, the alarm is explained by the burglar. Right? The burglar explains the alarm going off. So you're kind of back to your original low probability there being an earthquake because you've been told that yes, there's an alarm, but there's also a burglar. So you don't have to worry about, there also being maybe an earthquake as well causing the alarm because it's explained by the burglar. So this is the key point here, is that the probability of an earthquake given the burglary and an alarm is not the same as the probability of an earthquake just given the alarm. In other words, even though the earthquake and the burglar are marginally independent, they are not conditionally independent given the alarm. Now, if you want a real tough question, or harder, you can ask, are they conditionally independent given the fact that John calls? I won't bother with that today, but they're not, but we won't worry about proving that. Okay, but let's look at the other one too. So, John calling and Mary calling. Those events are not independent, right? Because they're correlated. If John calls, there's a good chance the alarm went off. Therefore, there's a good chance that Mary's going to call too. But they are conditionally independent given the alarm. So in this case, this is sort of the opposite case. Here, the probability that John calls, given Mary's calling and the alarm, is equal to the probability that John calls. Because the mechanics I described here were that if your alarm goes off, then both your neighbors call you just sort of randomly independent of each other. I kind of defined it that way. But importantly, they are not marginally independent, right? Because the probability that John calling, given that Mary calling, is probably a lot higher than the probability that John calls just by himself, right? Because if Mary calls, that means there's a good chance the alarm's going off, which means that there's a good chance John's going to call too, or a much higher chance John will call as well. Okay, so these are the actual important points sort of to take away here. Just an intuitive understanding about why, and kind of examples about why marginal independence does not imply conditional independence, and vice versa. Okay, any questions there? We're going actually even slower than I intended to, but that's not actually kind of expected, so oh well. Okay, so we're going to switch gears a little bit now and talk about a few more things before we talk about some distributions. We might get to those next time, I realize now. Okay. The first thing we're going to talk about is the notion of expectation. So expectation of a random variable is defined as expectation of a random variable x is equal to the sum over all possible values it can take on of that value times the probability that it equals that value. I could just write p, or just p at little x there. Now this is actually kind of, again, in wonderful notation. This number here, the expectation, despite being a function of a big x random variable, this is actually just a number. Right? This is some number. And we write it as a function of big X because it's a function of the entire. It wouldn't make any sense to say expectation of little x. I don't know what that would mean. It's a function of the entire distribution of the random variable, so we write it as a function of the whole random variable. But it's important to know that this expectation is not the same as p of x, which is a whole distribution. This is just a number, the expectation. The other important thing to emphasize is that this only makes sense if the values that x takes on are numerical. Right? The values, if the values are sunny, rainy, and cloudy, you cannot take an expectation of that variable. There's no notion of, sunny times 0.3 plus cloudy times 0.1, right? That doesn't compute. But if x takes on values of, numerical values of, 0, 1, 2, then you can take an expectation. This can also, of course, generalize to conditional independence. Sorry, conditional expectation. Expectation of x1 given little x2 would just be equal to the sum over all x1 times probability of x1 given x2, and so on. Now this is also a number. But importantly, if I were to write this, this is now a factor because I have to describe what this is. I'm summing over x1, but I have to describe what it is for all x2. Okay, so you have to be a little careful here. Again, notation is the hardest thing with probability. Okay, so let's just find a few rules of expectations. So the first rule is that expectations always add. So expectation of x1 plus x2 is always equal to the expectation of x1 plus expectation of x2. This happens whether or not x1 and x2 are independent or not. The proof here is very simple. The expectation of this thing is is just equal to, by definition, the I won't write it down again. I'll just sort of walk through this. You can look at the slides to see the proofs. It's equal to the sum over all values of x1 and x2 can take on of their joint distribution times the sum of those two things. Okay, that's the first line. In the second line, I just distribute this out over x1 and x2. So I have, x1 times this thing. I then move the x2 sum in here because it doesn't depend on x1, doesn't depend on x2. I do the same thing over here. I just, distribute that out. This is the x2 term. I move the sum of x1 there. This term and this term are just the marginal distributions. It's just marginalization. So this just equals x1 times the probability of x1. And that one there equals x2 times the probability of x2, which of course is just the expectation of x1 plus the expectation of x2. And notice that nowhere did I actually use the fact that they're independent or anything like that. Right? That applies to any distribution, whether they're independent or not. It's a very sort of powerful thing. Even when they're very correlated, you can still have linearity of expectation. By kind of a similar but different reason, when they are, but now only when they are independent, the expectation of a product is the product of expectations. And this happens because this is just the definition again. This will split up when they're independent. You can then separate out the sums, and you get the product of expectations. Okay. I think last slide. No, I have two more, but this is almost the last slide. The last kind of property we'll talk about is variance. The variance of a random variable x is equal to the expectation of x minus its expectation squared. Okay, so that's just equal to how much, kind of the expected deviation from, where deviation means the squared difference, from its expectation. And we can simplify this a little bit. So we can expand this out. This equals the expectation of x squared minus 2x, expectation of x, plus expectation of x squared. And now we use the linearity of expectation there. Say this is equal to expected value of x squared minus expected value of x times the value of x. The value of x times its expected value plus the expected value of x squared. Now, it's important to note that these are just numbers here, right? So this is just a number, okay? So it doesn't have any effect on the expectation. I mean, it just scales the expectation by that number. It's not a random variable, so we can just bring it outside the expectation. And so we can actually move all the numbers just outside the expectations. So this whole thing is equal to the expectation of this minus expectation of x times moving this out there, expectation of x. Sorry, I messed this up. This is x squared. And this, expectation of just a constant, just that same constant, nothing random about that. So this is then plus, sorry, this is a 2 here, plus the expectation of x squared. And of course, one of these cancel out with this one. So this just equals expectation of x squared minus the expectation of x squared. That's the variance. Now, this also generalizes to covariance between two random variables. So this one is just the covariance, this is just that definition, the covariance of between x1 and x2 is equal to the expectation of x1 minus its expectation times x2 minus its expectation. Which again, if you simplify it the exact same way as you did before, you get this is equal to the expectation of the product minus the product of expectations. And now actually we can see that, for variables that are not independent, this does not hold equality anymore, but in fact, this term here would be equal to this term plus their covariance. So again, these things are all a little bit, they're simple mathematically, but they are things that sort of are very useful when you find yourself manipulating probabilities. I think they're kind of cover most of what you'll actually see when people manipulate probabilities. Not all of it, certainly, but most of what you see. And so getting familiar with how to manipulate these things is important in practice. All right, so we have 5 minutes left. So kind of maybe to be expected to not get through even the already abbreviated lecture. That's okay. I want to mention 2 more things before I go, and that is the notion of infinite random variables. So the first thing is that if we have a discrete, but I shouldn't call it discrete, if we have what's called countably infinite random variables, like all the integers, we can have a distribution over all integers, and actually everything looks exactly the same as it did before. So the sums become infinite sums, that's true, but nothing else changes. So for instance, we can have a distribution over all positive integers, so the numbers 1 through infinity, where the probability, so x takes on value, is a random variable now that takes on values it takes on integer values. And the probability that x equals k will just be, for instance, 1/2 to the k. It's pretty easy to verify that that does in fact add to 1, right? You basically get the sum of x from 1 to infinity of p x equals k, which is equal to the sum from x equals 1 to infinity of 1 to the 2k, which just equals 1. So we have the desired probability. It is a distribution. And it's just an infinite distribution now. So of course you can't represent this anymore like a dictionary. You can actually represent it as a function, which is really all dictionaries are, right? They're just functions from keys to values. But everything else works kind of the same. Okay? It's just also a random variable. It is true that when x is continuous, though, things are a little bit different, sort of from a mathematical standpoint. But really, the only real difference for our purposes that you have to replace the sums with integrals now. So if x takes on values, say, in R, this thing here really is a function that will map from any real valued number, of course, to a density. I should actually clarify that. It is no longer mapping to a probability because now you can't sum over an uncountably infinite set. So instead what we need is we actually need something, it's not a probability anymore. This is actually now called, instead of a probability, this is actually called a probability density function. Density function. And the key point here, of course, again, you can't represent this as a dictionary anymore. Now it has to be represented as a proper function. But the key here, of course, is that the integral from negative to infinity of p of little x dx has to equal 1. So the analog of summing things up, we're now in continuous spaces integrating them, and the integral between negative infinity and positive infinity for real valued quantities is, of course, has to equal to 1. We can also think about probability. Of course, this is uncountably infinite, so the probability of actually, it's probability has probability 0 of actually ever being a specific value, right? All the values it takes on are, irrational and things like this. But if we want to know the probability that lies in a range, we can say the probability that, a less than or equal to x less than or equal to b would just be the integral over that range. And finally, there's a very common thing people sort of use, which is the probability, which is called the cumulative distribution function, written as f of a. This is just equal to the probability that x is less than or equal to a. That's just equal to the integral from negative infinity to a of px dx. So distributions, for instance, like the Gaussian distribution or the exponential distribution are very common examples of continuous random variables. And we will see these quite often in data science. So it's important to sort of be familiar with both types and have some passing familiarity with kind of how these things work in terms of density functions and cumulative distribution functions. Okay, so with that, we'll next time talk about some probability distributions, and we'll also talk a little bit about maximum likelihood estimation, hopefully.